is Daniel Florea, and today I'm presenting my final project for Tech 4230. The title of my presentation is The Future of DRM in Engineering. Digital rights management has traditionally been more associated with consumer media platforms. However, as modern engineering and industrial manufacturing move towards decentralized, data-driven ecosystems, securing intellectual property at the machine level has become a critical operational requirement. This presentation explores the systemic vulnerabilities of our current file protection methods and details emerging technical frameworks designed to safeguard industrial data from creation through physical fabrication. To understand why digital rights management has become essential, we must look at the structural value shift occurring across the industrial sector. Modern manufacturing has fully transitioned from legacy brick-and-mortar life cycles to a digital-first life cycle. Today, the core value of an industrial firm no longer resides merely in its physical factories, but in proprietary data structures and CAD files that drive automated production. Because this engineering data is inherently portable, it is highly vulnerable to unauthorized distribution. Without persistent protection, millions of dollars in research and development are exposed to industrial espionage and reverse engineering, which can ultimately introduce uncertified, counterfeit parts into critical infrastructure supply chains. Implementing an advanced industrial DRM framework addresses three core strategic priorities. First is IP integrity, which focuses on safeguarding millions of dollars in proprietary research and development man-hours from theft or leakage during external vendor handoffs. Second is supply chain safety, which establishes cryptographic checks to ensure that only certified original equipment manufacturer-designed specifications are executed by machinery when creating safety-critical parts. Third is monetization, where robust digital controls enable secure decentralized manufacturing models through automated pay-per-print authorization and subscription-based usage logic. To successfully protect an engineering workflow, a DRM system must actively secure three distinct classes of digital assets. The first layer consists of design assets, which encompass native 3D CAD models, structural assemblies, and proprietary finite element analysis material datasets. The second layer protects execution assets, which translates these designs into physical objects, including machine-specific G-code instructions, CAM toolpaths, and industrial slicing parameters for additive manufacturing. The third layer secures operational assets, including embedded device firmware, programmable logic controller code, and real-time digital twin telemetry loops that track properties such as structural stress and heat. Our current approach to access management relies almost entirely on defensive network parameters and hardware locking mechanisms. At the enterprise level, organizations use siloed product lifecycle management vaults. Systems such as Teamcenter utilize role-based access control inside corporate firewalls to restrict file visibility to authorized engineering nodes only. On the production floor, high-value applications rely on strict hardware handshakes. These configurations use node-locked licenses bound to specific machine identifiers, such as media access control, addresses, or physical USB dongles, to authorize local G-code processing. Despite these boundaries, current access systems remain vulnerable when files leave the home network. The primary flaw is that security is often completely lost when native CAD files are converted to neutral exchange formats like STEP or IGS for supplier use. Additionally, rigid digital rights management protocols create significant operational friction for field technicians in remote environments. In cases of network instability, requiring a continuous cloud connection to access basic diagnostic manuals can paralyze a workspace, leading to complete cessation of field operations. This brings us to the second half of our analysis, the future of industrial DRM. Moving forward, the engineering sector must transition away from passive network firewalls and move toward active file-level encryption and edge-based validation models that bridge the gap between digital intent and physical execution. The first major technical evolution is the implementation of next-generation enterprise DRM, or EDRM. EDRM delivers persistent file protection by wrapping engineering datasets in cryptographic security that actively survives format translation. Unlike traditional PLM vaults, the security parameters stay embedded inside the file itself, regardless of where it travels. This layer ensures that engineers maintain total control over their intellectual property, enabling remote revocation of access rights or complete blocking of local saving and duplication, even after data has been sent to a third-party vendor. Building upon persistent file encryption, blockchain architectures enable secure, decentralized manufacturing across untrusted supply networks. By using distributed ledgers, smart contracts can communicate directly with automated machine firmware. This integration unlocks proprietary G-code instructions for exactly the specific number of production cycles purchased by the vendor. The moment the authorized manufacturer runs complete, the firmware executes an automated script that re-encrypts or purges the file, preventing unauthorized overproduction or port cloning. To secure data during active fabrication, modern architectures leverage cyber-physical CNC security and telemetry loops. Edge cloud collaborative systems establish secure data exchange channels and run machine learning analytics across distributed manufacturing pipelines. By implementing live mechanical monitoring, such as vibration-based telemetry, the framework generates a real-time behavioral fingerprint of the active machining environment. This continuous integration of physical health intelligence protects sensitive data from malicious manipulation, unauthorized overrides, or data scraping during cloud tethering operations. This active feedback loop culminates in what we define as a digital twin enclosure. Through an automated ledger system, physical factory assets become permanently tethered to their virtual digital twin via continuous cloud loops. Access and operational authority are governed in real time by AI-driven behavioral telemetry. If a machine toolhead detects an anomalous vibration profile or flags an unauthorized data scraping script attempting to read coordinate paths, the CloudLink AI dynamically revokes the machine's firmware license, executing an emergency stop that freezes the physical machine instantly. To successfully implement these frameworks, I have outlined 3 strategic recommendations for engineering managers. First, we must standardize our systems by championing open standard encryption methodologies that allow protective metadata to persist seamlessly across different CAD formats. Second, we must architect resilient offline access models using time-bound localization tokens, ensuring that critical field service capability is never paralyzed by unexpected network connectivity drops. And finally, firms should implement a tiered IP structure, enforcing strict encrypted DRM for core proprietary designs while leveraging flexible Creative Commons frameworks for non-critical tooling innovations to foster supply chain collaboration. And to finish the presentation, here are a list of the references I used to put this together. I appreciate your time, and I hope you enjoyed this presentation. Thank you very much.